Trigonometry, double angles. Now we've seen how we can get formulae for compound angles. That is, the sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. And the cosine of a plus b equals the cosine of a cosine of b minus sine a sine b. And for tangent we've got the tangent of a plus b is equal to the tangent of a plus the tangent of b all divided by 1 minus the tangent of a times the tangent of b. We can also get some quite useful formulae simply by letting the angle b equal the angle a. Now this gives us the sine of a plus a is equal to the sine of a times the cosine of a plus the cosine of a times the sine of a. In other words, the sine of 2a is equal to 2 sine a cos a. Now we can do the same with the cosine formula. If we let b equal a, we get the cosine of a plus a is the cosine of a times the cosine of a minus the sine of a times the sine of a. In other words, the cosine of 2a is equal to the cosine of a all squared minus the sine of a all squared. Cos 2a equals cos squared a minus sine squared a. But we have sine squared a plus cos squared a is equal to 1, which can be rearranged as minus sine squared a equals cos squared a minus 1. And if we substitute minus sine squared a in the above formula, we get cos 2a equals cos squared a plus cos squared a minus 1, which is cos 2a equals 2 cos squared a minus 1. But we can also write cos squared a equals 1 minus sine squared a. And when we substitute that into cos 2a equals cos squared a minus sine squared a, we get cos 2a equals 1 minus sine squared a minus sine squared a. Or the cosine of 2a equals 1 minus 2 sine squared a. By letting a equal b, we can also get the tangent of a plus a is equal to the tangent of a plus the tangent of a, all divided by 1 minus tan a tan a. This simplifies to the tangent of 2a is equal to 2 times the tangent of a over 1 minus tan squared a. So we have 5 useful formulae. The first one is for sine 2a. Sine 2a is equal to 2 sine a cos a. The next 3 are all for the cosine of 2a. We can write the cosine of 2a is equal to cos squared a minus sine squared a, or the cos of 2a is equal to 2 cos squared a minus 1, or the cosine of 2a is equal to 1 minus 2 sine squared a. And for tangent we have the tangent of 2a is equal to 2 tan a divided by 1 minus tan squared a. Now all of these formulae turn out to be very useful in different situations, so they are worth learning. Let's have a look at an example. Example 1. Solve the cosine of 2 theta plus the cosine of theta is equal to 0 for theta lying between 0 and 360 degrees. Well, to solve this, we've got the cosine of 2 theta plus the cosine of theta is equal to 0. Now here we've got cosines of theta and cosines of 2 theta. It would help if we could get everything in terms of just cosine of theta. So we can write the cosine of 2 theta is equal to 2 cosine squared theta minus 1. So we have 2 cosine squared theta minus 1 plus cosine theta equals 0, which can be rearranged as 2 cos squared theta plus cos theta minus 1 equals 0, which is a quadratic equation in cos theta. Now we can factorise the equation as 2 cos theta minus 1 times cos theta plus 1 equals 0. Now that means 2 cos theta minus 1 is equal to 0, or cos theta plus 1 is equal to 0. So cos theta is equal to a half, or cos theta is equal to minus 1. Now if cos theta is a half, then theta is 60 degrees or 300 degrees. And if cos theta is minus 1, then theta is equal to 180 degrees. So our answer is theta is 60 degrees or 300 degrees or 180 degrees. In example 2, we're asked to show that the cosine of 2 theta times 1 plus tan squared theta is equal to 1 minus tan squared theta. Well, when trying to prove an identity like this, it's always best to start with the more complicated side and try to work towards the simpler side. So it's best to start with the left-hand side, which is the cosine of 2 theta into 1 plus tan squared theta. Now on the left-hand side we've got expressions involving 2 theta, but on the right-hand side we've only got expressions involving theta. So the important thing to do is eliminate the 2 theta. Now we can change the cosine of 2 theta into 2 cos squared theta minus 1. So we've got 2 cos squared theta minus 1 into 1 plus tan squared theta. Now we can expand those brackets to get 2 cos squared theta plus 2 cos squared theta tan squared theta minus 1 minus tan squared theta. Now in that expression we've got a tan squared theta, and that can be changed into sine squared theta over cos squared theta. Now the cosine squared theta that we get cancels with the cosine squared theta before it. So we're left with 2 cos squared theta plus 2 sine squared theta minus 1 minus tan squared theta. But we could factorise the first two terms as 2 into cos squared theta plus sine squared theta, and then we've got minus 1 minus tan squared theta. Now cos squared theta plus sine squared theta is equal to 1, and so that leaves us with 2 minus 1 minus tan squared theta, which is 1 minus tan squared theta, which is the result that we want. In 3 part 1 we're asked to simplify 1 minus cos 2 theta over sine 2 theta. Now we have 1 minus cos 2 theta over sine 2 theta. The cos 2 theta can be written as 1 minus 2 sine squared theta, and the sine 2 theta can be written as 2 sine theta cos theta. Now that gives us 1 minus 2 sine squared theta all over 2 sine theta cos theta, which simplifies to 2 sine squared theta over 2 sine theta cos theta. Now the 2's cancel and the sine theta cancels top and bottom to leave sine theta over cos theta, which is equal to the tangent of theta. Now in example 3 part 2 we're asked to solve the equation 3 cos 2 theta plus 5 sine theta equals 4, with theta lying between 0 and 180 degrees. Well, we start with 3 cos 2 theta plus 5 sine theta equals 4. Now this involves expressions with 2 theta and with theta, so we need to put them all in terms of just theta. And we can change the cos 2 theta into 1 minus 2 sine squared theta to get 3 minus 6 sine squared theta plus 5 sine theta minus 4 equals 0. And 3 minus 4 is equal to minus 1, so we've got minus 6 sine squared theta plus 5 sine theta minus 1 equals 0, or if we multiply all the way through by minus 1, that gives us 6 sine squared theta minus 5 sine theta plus 1 is equal to 0. Now that's a quadratic equation in sine theta, so we can factorise it as 3 sine theta minus 1 into 2 sine theta minus 1 equals 0. Now that means either 3 sine theta minus 1 is equal to 0 or 2 sine theta minus 1 equals 0, which means sine theta is a third or sine theta is a half. Now, if sine theta is equal to a third, that means theta is 19.47 degrees, or 180 minus that, which is 160.53 degrees. If sine theta is equal to a half, then theta is equal to 30 degrees or 150 degrees. So we have theta could equal 19.5 degrees or 160.5 degrees or 30 degrees or 150 degrees. One important use of the cosine double angle formulae is to integrate expressions such as sine squared x or cos squared x. We can see this in the following example, example 4. In part 1 we're asked to integrate cos squared x dx. Well, to do this we can use the fact that cos 2x is equal to 2 cos squared x minus 1, and that can be rearranged as 2 cos squared x equals cos 2x plus 1, or cos squared x equals a half into cos 2x plus 1. Now that means the integral of cos squared x dx can be written as the integral of a half cos 2x plus 1 dx. And we can take the half outside the integral sign to give us that it's equal to a half the integral of cos 2x plus 1 dx. Now the integral of cos 2x is a half sine 2x, and the integral of 1 is x. So we have the integral is equal to a half into sine 2x over 2 plus x, plus a constant. So we have the integral of cos squared x is equal to a quarter sine 2x plus a half x plus c. Now in part 2 we're asked to integrate sine squared x dx. Now this time we can use the fact that cos 2x is equal to 1 minus 2 sine squared x. In other words, 2 sine squared x is equal to 1 minus cos 2x, or sine squared x is equal to a half into 1 minus cos 2x. So the integral of sine squared x dx is equal to the integral of a half into 1 minus cos 2x dx. Now we can take the half outside the integral sign to give us a half the integral of 1 minus cos 2x dx. Now the integral of 1 is x, and the integral of cos 2x is sine 2x over 2. So we've got the integral is equal to a half into x minus sine 2x over 2 plus c, and so the integral of sine squared x is equal to a half x minus a quarter sine 2x plus c. Sometimes the double angle formulae appear unexpectedly in different situations. It's useful in that case to be able to recognise them, as it sometimes simplifies the work. We see that situation arise in the next example, which is a mechanics problem. When a ball is struck from level ground with a velocity v at an angle of theta to the horizontal, then the horizontal distance travelled, x, and its height, y, are given by the formulae x is equal to vt cos theta and y is equal to vt sin theta minus a half gt squared, where g is the acceleration due to gravity. Now the range of the ball is the horizontal distance it travels before it strikes the ground. We are asked to show that, to get the maximum range, it should be struck at an angle of 45 degrees, and then find what that maximum range is. Well, to solve this, we've got x is equal to vt cos theta, which can be rearranged to give t equals x over v cos theta. Now we can substitute t in the equation y equals vt sin theta minus a half gt squared. And this gives us y equals v into x over v cos theta times sin theta minus g over 2 into x over v cos theta all squared. Now we can cancel the v's in the first term and simplify it to give y equals x into sin theta over cosine theta minus gx squared over 2v squared cos squared theta. Now when the ball strikes the ground again, we have y equals 0. So we can write x into sin theta over cos theta is equal to gx squared over 2v squared cos squared theta. And if we multiply all the way through by 2v squared cos squared theta, this simplifies to 2x v squared sin theta cos theta equals gx squared. Now we can cancel the x terms and rearrange that as v squared times 2 sin theta cos theta is equal to gx. Now we notice that 2 sin theta cos theta is equal to sin 2 theta. So we have v squared times sin 2 theta equals gx, or x is equal to v squared over g times sin 2 theta. Now the maximum value that sine ever takes is 1. So the maximum value of sin 2 theta is 1 when 2 theta is 90 degrees. Now that means theta is 45 degrees. So the maximum value of x is v squared over g when theta is 45 degrees. In this case, recognizing the double angle formula towards the end of the question simplifies the last part. Now we have seen the double angle trig formulae. We could, if we wanted to, extend these to get triple angle formulae. So in example 6, we're asked to find the formulae for sine of 3a in terms of sin a, cos of 3a in terms of cos a, and tangent of 3a in terms of tan a. So in part 1, sine of 3a could be written as sine of a plus 2a, which is sin a cos 2a plus cos a sin 2a. Now the cos 2a can be written as 1 minus 2 sin squared a, and the sin 2a could be written as 2 sin a cos 2a. Now that simplifies to sin a minus 2 sin cubed a plus 2 sin a cos squared a. But cos squared a can be written as 1 minus sin squared a. So that simplifies to sin a minus 2 sin cubed a plus 2 sin a minus 2 sin cubed a. Now this can be simplified down to give us sine of 3a is equal to 3 sin a minus 4 sin cubed a. Now in part 2 we're asked to find the formula for the cosine of 3a. Well, we have the cosine of 3a can be written as the cosine of a plus 2a, which is the cosine of a cosine of 2a minus the sine of a sine of 2a. Now the cosine of 2a can be written as 2 cosine squared a minus 1, and the sine of 2a can be written as 2 sin a cos a. So we have 2 cos cubed a minus cos a minus 2 cos a sine squared a. Now the sine squared a can be written as 1 minus cos squared a. Now when we expand the brackets we get 2 cos cubed a minus cos a minus 2 cos a plus 2 cos cubed a. And that simplifies down to give us that the cosine of 3a is equal to 4 cos cubed a minus 3 cos a. Now in part 3 we're asked to find a formula for the tangent of 3a. Well, the tangent of 3a can be written as the tangent of a plus 2a, which is tan a plus tan 2a all over 1 minus tan a tan 2a. Now the tangent of 2a can be written as 2 tan a over 1 minus tan squared a, both on the top and on the bottom. Now if we multiply the top and the bottom by 1 minus tan squared a, we get tan a into 1 minus tan squared a plus 2 tan a all over 1 minus tan squared a minus 2 tan squared a. Now that simplifies down to give us the tangent of 3a is equal to 3 tan a minus tan cubed a all over 1 minus 3 tan squared a.